In this video I'll go through some examples of matrix algebra taken from the notes exercises 1.41 on page 7. To get the most out of this video, I would suggest that you pause it at the beginning of each question, try the exercise yourself, and then watch the solution here. So the first one gives us a matrix A 2 by 2 and asks us to show that a squared plus 2a minus 11 times I is equal to 0. So first I'll get those three matrices a squared, 2a and 11i, and then I'll add them up. So first a squared is just equal to a times a. So there's a written down twice to multiply them together. So my first element is going to be 1 times 1 plus 2 times 4. First row times first column. Next I'll do the first row times the second column. So that's going to be 1 times 2 plus 2 times minus 3. Next I will do a second row first column. So again that's down here in the second row and the first column of this matrix. It's going to be 4 times 1 plus minus 3 times 4. And you can see there I've just put that minus 3 in brackets. Next I'll do second row and second column down here. So that's 4 times 2 plus minus 3 times minus 3. Now I'll just do that multiplication. So in position 1, 1 here, first row, first column, 1 times 1 is 1, 2 times 4 is 8. 1 times 2 is 2, 2 times minus 3 is minus 6, 4 times 1 is 4, minus 3 times 4 is minus 12, 4 times 2 is 8, and minus 3 times minus 3 is plus 9. And finally I add those up. 1 plus 8 is 9, 2 minus 6 is minus 4, 4 minus 12 is minus 8, and 8 plus 9 is 17. So there is the matrix A squared. Next I'll get the matrix 2 times A. So there's my A matrix written in again, 1, 2, 4, minus 3, and I multiply it by 2. And the way you multiply a matrix by a scalar being just a number, here it's 2, you just multiply each element by that number. So that's equal to 2 times 1, 2 times 2, 2 times 4, and 2 times minus 3. So there's the matrix 2a, I'll just multiply them out. That's 2, 4, 8, and 2 times minus 3 is minus 6. So there's the matrix 2 times a. Finally, we need the matrix minus 11i. So I means the identity matrix. That's just a matrix with 1s all down the diagonal and 0s everywhere else. In this case we know that I must mean a 2 by 2 matrix because we're adding it on to another 2 by 2 matrix, and you can only add matrices if they're the same size. So in this case I'll write down my minus 11 first. The I matrix that I'm using must be this one. 1s on the diagonal, 0s everywhere else, and 2 by 2. If you recall from the notes, the I matrix is the one that if you multiply it by another matrix you get that same matrix back. For example, any matrix A times I is equal to A, and I times any matrix A is also equal to A. So that's the matrix with that special property. It's like multiplying by 1 if you're just doing normal numbers, in that multiplying by I doesn't change the matrix. Now in this case we want minus 11 times I. So we multiply minus 11 by that matrix and we get this one. Minus 11, 0, 0, minus 11. So now I have my three matrices, a squared, 2a, and minus 11 times I. So now I can just add those all up. Here I have my original question, a squared plus 2a minus 11i, and I filled in those three matrices. So there's your a squared, your 2a, and your minus 11i. Now for that last term I've put plus here because I know it's minus here, but I've put that minus 11 inside the matrix. So, that's the same as saying plus and then all this in brackets. So I put that minus 11 inside, so that's a plus here. And then to add up matrices, they're all the same size, so they will add up. You just add them term by term. So in the top left, that's position 1, 1, first row, first column. I have 9 plus 2 minus 11. Below that, in position 2, 1, that's second row, first column, I have minus 8, I have plus 8, and I have plus 0. In the top right, that's position 1, 2, I have minus 4, then 4, and 0. And in the bottom right, that's position 2, 2, or second row, second column, I have 17, I have minus 6, and I have minus 11. Now finally, we just add up each element to get an answer. So 9 plus 2 minus 11 is 0, minus 4 plus 4 is 0, minus 8 plus 8 is 0, and 17 minus 6 minus 11 is 0. And if you remember, the question originally asked to show that that thing on top equals 0. Now we didn't get the number 0, we got a matrix that was all zeros. So, but in this case that's implied by the fact that you have an equation with matrices. Obviously it must equal a matrix. So when they say 0 there, they must mean a 2 by 2 matrix full of zeros. So here's the second question there. So we're given a matrix A, which is 3 by 3, and we're asked to look at A plus A transpose and A minus A transpose. So the first question is, what is A transpose? The transpose of a matrix is like its mirror image along the diagonal. Or you can get the transpose of a matrix by swapping the rows with the columns. So for example, for this matrix A, the first row is 1, 2, 4. So for A transpose, the first column is going to be 1, 2, 4. The second row of A is minus 2, 3, 5. So the second column of A transpose is minus 2, 3, 5. And the last row there is 2 minus 1, 2. So it goes here in the last column. And if you look at that, you can see that the diagonal hasn't changed. And what's happened is everything has swapped places around the diagonal. So this minus 1, 5 here have swapped. That 2 and that 4 have swapped. And minus 2 and 2 here have swapped around. So it's like you flipped the whole thing over around the diagonal. So first we're asked to show that the matrix P, which we're told is just A plus A transpose, is symmetric. So what does symmetric mean? It means that elements opposite each other on the diagonal are the same. So for a symmetric matrix, if I have a 4 here, I would need to have a 4 here as well. Or a 5 here, I would have to have a 5 here as well. Then it would be symmetric. So I'm going to calculate it in a second, but let's just look at this first. A plus A transpose. If you think about it, the element down here, say, in any matrix plus its own transpose, is going to be the one here in the bottom left plus the one from the top right. And up in the top right, when you add together the matrix and its transpose, you're going to get the same thing. You're going to get the one that was originally up here plus the one from the other side. So in this case, in both the bottom left and the top right position, we're going to get 6. If you think about it, you can see that for any matrix, if we take the matrix plus its own transpose, if you look at either side of the diagonal, you're going to be getting the same thing on both sides, because you're just adding together the same two numbers. So this will be generally true for any matrix. So let's just check that it's true for this specific one. So there I've written it down. So to add two matrices together, you just add them term by term. So in the top left there I have 1 plus 1 is 2. Then I have 2 plus minus 2 is 0. 4 plus 2 is 6. 2 plus minus 2 is 0. So that's nice and symmetric. 3 plus 3 is 6. 5 plus minus 1 is 5 minus 1 is 4. 2 plus 4 is 6. So again, nice and symmetric. I get 4 here, symmetric, and I get 4 here. So we verified there that that is symmetric. So 0 matches a 0, 6 matches a 6, 4 matches a 4. The next thing we're asked to show is that A minus A transpose is anti-symmetric. Now what anti-symmetric means is that when you look at opposite positions like this, that one should be minus the other. And if we think about this, this should actually be true for any matrix A, no matter what the numbers are. Because if I look, let's say there's 2 here, I'm going to say 2 minus 4 on one side, and on the other side it's going to be 4 minus 2. So one will be minus the other. So again, that will be true for any matrix A, not just this one, but we'll check it now for this one. And as we go through it, you might be able to see why it's true for every matrix. So here I've written A minus A transpose. And again, I'll add these all up. So I'll have 1 minus 1 in the top left. I'll have 2 minus minus 2 here, so be careful with those minuses. And I'll have 4 minus 2 here. So second row, I'm going to have minus 2 minus 2. I'll have 3 minus 3. And I have 5 minus minus 1. Bottom row, I have 2 minus 4. And you can see at this point some symmetry. See, I had 4 minus 2 here, I have 2 minus 4 here. So one of those will turn out to be minus the other. Then I have minus 1 minus 5. And I have 2 minus 2. So now I'll just work out each of those. 1 minus 1 is 0. So 2 minus minus 2. So minus minus is plus. That's 2 plus 2 is 4. 4 minus 2 is 2. Then next row I have minus 2 minus 2, which is minus 4. So that's nice and anti-symmetric. I have 4 and I have minus 4. 3 minus 3 is 0. 5 minus minus 1 is 5 plus 1 is 6. 2 minus 4 is minus 2. Minus 6 and 0. So this is anti-symmetric in that when you look at the mirror images across the diagonal, you get minus the same number. So 2 and minus 2, 4 and minus 4, 6 is minus 6. So there's our two matrices P and Q. That's A plus A transpose and A minus A transpose. And we're asked to show that we can express A as a sum of P and Q. So let's just check for a second. What if I just say P plus Q? Well, without writing down the matrix in full, that's going to be A plus A transpose, right? That's P, and Q is A minus A transpose. So what I've got there is actually A plus A transpose minus A transpose. So that's just A plus A, or 2A. So if I just want A, let's solve this equation for A. I could bring that 2 across. So a half of P plus Q should be equal to A. Or I could express A. I'll say A is equal to, let's call it a half times P plus a half times Q. Now we're looking at a particular matrix A here, but you could actually do this for any matrix, in that you could express it as a sum of a symmetric matrix and an anti-symmetric matrix. So any square matrix that you encounter you can break it up into a sum of a symmetric and an antisymmetric matrix. And specifically how you do that is you take a half of A plus A transpose plus a half of A minus A transpose, and that gives you your symmetric and your antisymmetric matrix that you can combine to get back your original A matrix. So let's show it now specifically for the A that we're given. So I've written down a half P and a half Q there. So, a half a symmetric matrix is still symmetric, and likewise for antisymmetric. So I've written down a symmetric and antisymmetric matrix there that when I add them together, I'll get back A. So the actual adding up of that I will leave to you to check. Here's another example, part C. So I'm asked to get A times B transpose, and B transpose times A transpose. So let's multiply them out first. A times B equals. So they are both 3 by 3 matrices, so their product will also be a 3 by 3. So we have first row times first column. That is this row by this column. So we will have 1 times 1, 2 times 1, and 2 times minus 1, and add all those up. So I'll do it a bit quicker this time. So first row times first column. 1 times 1 is 1, plus 2 times 1 is 2, plus 2 times minus 1 is actually minus 2. Now I'll go down that first column. So second row first column here, position 2, 1. I'll multiply second row here by first column here. So I'm going to get 0 times 1 is 0, 1 times 1 is 1, and 1 times minus 1 is minus 1. And then third row, so this is going to be third row here, again by the first column here, going in here. So that's going to be 1 times 1 is 1, 0 times anything is 0, and 1 times minus 1 is minus 1. So now I'm going to go to the second column, so I'll be using this column here, second column. So again I'm going to go first, second, third row by the second column. So 1 times minus 2 is minus 2, 2 times minus 1 is minus 2, and 2 times 2 is 4. Then second row, 0 times minus 2 is 0, 1 times minus 1 is minus 1, and 1 times 2 is 2. And I'm just going to fill in the rest of them now. And if you add all those up, you'll find that what you have is 1, 0, 0, 0, 1, 0, 0, 0, 1. Which is the 3 by 3 identity matrix. So next we're asked for A times B transpose. So that's just the transpose of the matrix we just found, which, since the identity matrix is a symmetric matrix, it's equal to its own transpose, because everything is the same across the diagonal. So this is actually just equal to the same thing again. I'll call it I here. This is I here. So it's the same thing again. Finally, we're asked for B transpose times A transpose. Now, there's a special property of transposes that we can use here. It's generally true that B transpose times A transpose is equal to A times B transposed. So if you want to get the transpose of a product, like A times B, it's the transpose of B times the transpose of A. Don't get these mixed up, because remember that for matrices, it matters which order you multiply them in. So AB is not the same as B times A. In general, A times B is not the same thing as B times A. So A times B transpose is B transpose times A transpose. So that identity is there in the notes as well. So knowing that, the third part of this is very easy, because we already have A times B transpose. It is the 3x3 identity matrix. So the answers for all these three questions are the same, and it's this very simple identity matrix with ones down the diagonal and zeros everywhere else. So I will leave the rest of those exercises to you, and if there's any you can't get the right answers for, ask me in the tutorial.